Swayam Prabha. Digital India. Educated India.
In this lecture, we will discuss about the applications using machine learning techniques. For example, if you have last class we discussed about various problems, right. For example, how to classify different types of proteins. What are the different classification problems?
Classification, real
right, DNA binding or not, are the transmembrane proteins or not, right, are the transmembrane helical proteins or beta viral proteins, are the driver mutation or passenger mutations. Also for image processing we discussed whether this can be a malignant or it is a benign, right. So, we discussed various aspects in the classification problems. Then again also we discussed about the other real value problems. So, for example, if you take solvent accessibility, either you can classify is buried or exposed, or you can predict the exact values, that is 15.5 angstrom square and so on. So, then we discussed about the various aspects we have one has to consider for developing any algorithm, right. What are the various important aspects we have to consider? First one is data set. So, data should be unbiased, non-redundant, right, and reliable data set, right, with the different various range of these values. Once we have the data set, then we can derive the features. So, we have to be cautious and should be very aware that the features what you extract, that should be applicable to what your problem, right. So, if you for example, if you take about the DNA binding proteins, right. So, you should know there are some bias in the positive charge residues. Likewise, you have to choose the features, right, that should be applicable to your problem. Then once we select the features, then we need to extract and as well as the choose what are the important features. For example, if few features are very closely related, for example, the correlation is 0.95, then you introduce a bias because you are using the same feature 2 times. So, you need to select the features which are important as well as which can explain or which can discriminate or distinguish different types of proteins. Then once we select the features or once we extract the features, then we use the different methods like the statistical methods or machine learning techniques, right, to discriminate or to classify the different types of proteins or different applications. Once we make the method, then we need to assess. We use various measures to assess the performance. What are the various measures?
accuracy,
sensitivity, specificity, accuracy, ROC, right, precision, recall. So, we use various measures to assess the performance of the method. We have to be sure that accuracy is only not the only measure, right. We need to check about the sensitivity as well as the specificity to see whether the method is performing well or not. Then the various validation procedures, like we can see the back check or the self consistency or n-fold cross validation or jackknife, split sampling and so on. So, we can validate all these things. Then once if you are satisfied with your method and the performance, then you can develop a web server, right, for the applications. So, it can be used for others. So, among all these classifications, today I explain one of the applications, right, mainly with the statistical methods as well as the machine learning techniques to classify 2 groups of proteins, right. This will give you more details what are the various aspects we have to consider for developing any algorithm, right, on any applications. Here I mentioned 2 different types of proteins, right. One is the transmembrane helical proteins and the transmembrane strand proteins. We already discussed in the previous classes about the transmembrane proteins, right. What are the transmembrane proteins? Right, the proteins which are embedded into membranes, right, the biological membranes. So, you can see this is a membrane part, right, this is embedded into membranes. So, here discuss 2 different types of membrane proteins, right. This one you see the inside the membrane, this is helical, right. So, this type of proteins we call as transmembrane helical proteins. If you see second type, here if you see this is the protein which contains the beta barrel, right. So, these proteins we call as transmembrane beta barrel proteins or transmembrane strand proteins, right. So, abbreviation I use TMH and TMS, right. If you have a pool of proteins, can we identify the proteins, right, which belong to the helical ones or which belong to the strand ones. So, there are various methods to do this. I will explain two different methods, mainly the statistical methods and the machine learning techniques. How to do that? Right? What is the first step we have to do? Data set, right? First we have to get a data set. So, if you have a data set, then maybe you can derive the features from the data set, right. So, here first I explain about the method what I already discussed earlier. So, when you have a data set, this is your standard data set A and B, right, you can derive the features. For example, here I show the amino acid composition, right. So, if we calculate this amino acid composition, let us take that this node. Then for any protein X, right, for calculate the composition, compare with the class A, for example, TMH, or compare the class B, this is TMS, and see the deviation. If the deviation is less in the case of B, this is the transmembrane strand proteins, very less in A, then is a TMH protein, right, that is fine. Okay. So, for getting this information, right, to get the standard values, we need to have a standard set of data, right. So, in this case we have to get a data set. So, we can have various resources to get the data. We discussed about various data sets, various what are different databases we discussed? PDB is for protein structures, for the DNA sequences, GenBank or DDBJ, protein sequences, right, Uniprot, right, like for stability data, Protham. So, we discussed various databases. Here our aim is to classify transmembrane helical and strand proteins, right. You can get the data from protein data bank. Also there are several databases which are specifically mentioned for the transmembrane proteins, right, TM topo or PDB-TM and so on. So, here PDB-TM, it is they are updating quite frequently, given there is a recent update, right. So, we use the PDB-TM, this is the protein data bank, the same PDB, protein data bank of transmembrane proteins, right, this is how they abbreviate the PDB-TM. So, this database you can see different types of transmembrane proteins, either helical type or the beta viral type. Also it has various options to extract the data based on the number of helices, number of strands, right. Also they have developed a program to identify the regions where the residues which are located in the membrane or extracellular space, right, and so on. So, they also have the option to download the data based on the non-redundant data sets for the sequences as well as the structures. So, currently we have the transmembrane proteins, right, this is the about 3000 alpha as well as about 300 beta viral proteins. So, if they go the download option, right, so there you can get the redundant alpha and the non-redundant alpha, right, also the redundant beta and non-redundant beta, right. So, first we take all the redundant ones. If you get the redundant data, then we need to get the non-redundant ones, right, or you can get the non-redundant, but here they use a specific cutoff either 30% or 40%, right. Sometimes we like to have a specific cutoff as per our desire. In this case we need to download the redundant data, that means we will get all the data. Once we get all the data, then what you have to do? You have to take the non-redundant data set, right. Now, if you go to PDB-TM, we will get the all the sequences of transmembrane helical proteins and TMS proteins, right, that is fine, data set is done. Then you have to remove the redundancy, right, to reduce redundancy we discussed about various methods. What are various methods we discussed earlier to reduce redundancy? Clustering, you can see CD hit, blast and the Pisces, various methods we discussed, right. So, we say CD hit, right, we will have the lot of options. Also we discussed about the command what we have to give, right, in the CD hit to get the non-redundant sequences. You can specify the word size, you can specify the redundancy, right. Also then if you give the input files and output files, you can get that. So, these are the various options available in the CD hit, right. Also you can see the net online also you can reduce redundancy using CD hit. So, you ask for the sequence identity cutoff, right, the word size. So, then you can get the non-redundant sequences. So, for example, if you want to have 30% redundancy, you can use the 0.3. So, you can get the non-redundant sequences. First we get the sequences, for this case we use PDB-TM, and once we download the sequences, then reduce redundancy, right, at any cutoff. for example 30% cutoff, we can use CD-HIT to get the sequences with 30% cutoff. So, now we need to think about the features. What are the various features we can derive from the sequences and which features will be meaningful and applicable to these types of proteins, right. One of the features you can think about, there is hydrophobicity, because if you see the transformed helical proteins, the transformed regions are enriched with the hydrophobic residues. So, you can expect that these residues are highly hydrophobic nature. Then this hydrophobicity you can see in the composition, right, because if you see the transformed region, these regions are enriched with leucine, alanine, valine, right, this aroma and as well as aromatic residues. So, composition could be also be another important feature to classify these two types of proteins, right. So, let us see how to get the composition. How to calculate the composition? Right, take the N of I for 20 residues divided by N is the total number of residues in a protein, right. So, here I show the data for the different amino acid residues. You can see this is the different 20 amino acid residues, we have the values. Okay. Here if you see this for the data for the all alpha the TMH proteins, right. Here we have data for the TMS proteins. If you compare the values, you can see some residues are dominant in the alpha proteins and some of them in the TMS proteins. For example, if you see the leucine, this is the 0.114 or 0.15, right, but in the case of beta, you see this is even sometimes it is very less 0.04, 0.05, 0.06 and so on. Likewise, some other residues, right, for example, if it is the valine or the tryptophan, you can see the difference, right. We discussed earlier right about the composition for the different proteins. So, you can take the composition, what could be an important feature to classify these two types of proteins, right. I will show you the results, right, what is the prediction accuracy or performance if you use the composition as the feature. First we talk about the statistical methods, right. So, now we can get the overall composition. They take for example, if you have the 500 proteins or 1000 proteins, take all the proteins and you can take the overall composition, right, for the case of the helical proteins as well as for the TMS proteins, fine. Then once you have this composition, then take the new protein, protein X, where we take a protein X, then you can calculate the deviation, right. You can see either the Euclidean distance or you can do the Hamming distance, right. So, what is Hamming distance? How to calculate the Hamming distance?
The difference.
Difference, right? Composition of A minus composition of X, right. So, you can see this is sigma I equal to 1 to 20, right. If you take the set of proteins, this composition of the whole proteins A, and for any X, right, I equal to 1 to 20, right, you can take this I. So, you can do it at 20 residues, right, take the absolute values, the difference, you can get that. For the case of the Euclidean distance, you can use this equation, right, square root of I equal to 1 to 20, right, for the case of the all alpha TMH proteins, right, this is the TMH, right, this for the any protein for your query protein. Likewise, you can do for the TMS and your query protein here, this is your query protein, right, get the difference, square of the difference and sum up and take the square root, then you will get the d alpha I and d beta I. Then you compare these two, d alpha I and d beta I, right, either you get obtained from Euclidean distance or you obtain from the Hamming distance, then it will tell you whether your protein is of TMS or the TMH. For example, if this is the value, okay, you can see the actual class, alpha it is 15, this beta it is 0.19, it is 0.15, 0.19. So, what is the predicted class?
Alpha.
TMH, right, this TMH. Second one?
TMH.
TMH. Third one?
TMH.
TMH. Fourth one?
TMH.
TMH. This one?
TMS.
TMS, 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 because this is less here, here this is less, right. Compare these two numbers and see which one is less, right, that you have the predicted class, because 0.15, this is less than 0.19. So, this is TMH. So, we put the assign the class TMH. So, if you do this, so you can see this perfectly matching. So, you can see the all the examples, right, 8 examples, you can get the full results, right. You can calculate assess with sensitivity, specificity and accuracy, right. So, what is the case sensitivity here?
100%.
100%, right. So, this is 4 by 4, this is equal to 100, 4 by 4, this is equal to 100%. Specificity is equal to 100%. Accuracy 8 by 8, this is equal to 100%, right, fine. So, this is fine. Okay, so, you can do this. So, here we use 8 data, right. Likewise, you can use all the data as a training and you can evaluate the performance using training. Then you make it as 2 groups. First is say 60%, 60% we use to get the composition for the TMH and the TMS. Then remaining 40% we use to test, right, use the same values, you can get the 40% of the data. Each protein in this 40% you can test and then see whether these proteins are also correctly identified as TMS or the TMH, right, then you can evaluate the performance. Then sometimes if you have a minor deviations, for example 0.1 or 0.05, see for small deviations the performance will be less. In this case you can add an error function, instead of you can compare the sigma I of A and sigma I of B, right, with any x, right, you can add a error function, for example this is 0.05. So, then you increase you change error function and you can optimize your method so with the highest performance, right. You can do that. In this case you can get the method with the better performance than just using the difference between the sigma A and sigma B with the protein X, right, you can do that. So, this is statistical method you can do with that, right. This you have to derive your features and you have to use your features by yourself and you have to assess the performance and the error function also you have to choose and you have to tune the parameters and optimize the method. So, likewise this another type of techniques, that is machine learning. So, in this case you do not have to worry about all these things. If you collect a set of features, the machine learning will learn your input data as well as with respect to the output and this will choose the important features and also it will train in such a way that your input will be mapped with the output with the highest performance. Last class also I discussed little bit about the machine learning techniques, right. This class I will go for a little bit more details, or for additional details you can take a class given the computer science courses. Okay, what is x here? X is your input, so y is your output, right. Here it will say learning algorithm, that your task is you have to discriminate this type of proteins in x, right, into y whether it is TMS or TMH, right. So, how do we know whether this algorithm, the program learn from this experience? So, if you set to learn from the experience, right, this experience you can see E, right, for any task. What is our task here? Classifying the transmembrane helical and transmembrane beta barrel proteins, right. So, with respect to the performance, so performance, what are the various performance we discussed? Sensitivity, specificity, accuracy and so on, right. If this learns only if is the performance, right, on this task, right, measured by the any p, right, it improves the experience E. If it gets information, right, based on the experience, the learning algorithm, if it increase the performance, then we say that okay, the program learns, right, from the experience C with respect to our task class T, that is classifying transmembrane helical and strand proteins with respect to the improvement in the performance P, for example accuracy, right. That means it learns only if the performance increases for our own task. So, what are various applications in machine learning? So, machine learning has wide range of applications, not only in biology, in all aspects of in the system, right. So, lot of applications, for example in the data mining, we can learning from very large data sets, right, maybe we can take in physics or the chemistry or the any engineering sides, whatever. So, it learns from very large data set and you can derive the features to get what the performance we require. For example, if you see the recognition of complex machine inputs, like handwriting, language and image recognition, right. You can read these images and then we can correctly tell that okay, this is what they mean, right, different handwriting languages. Then we also in the self adapting programs like recommendation systems as well as modeling complex systems, right. For example, the brain. So, you can see the several neurons, right. You can use for example, the artificial intelligence, right. You can model these complex systems, right, using different machine learning techniques. Then what are the various learning algorithms? There are various learning algorithms, right, for this machine learning. For example, linear regression or logistic regression, decision tree. This will classify this data. Okay, if A is more than B, so it can be this one. Then compare with the D. So if this A is less than D, then it could be the group another group. Likewise, it compare various features. Then finally, this will make a tree, right. And finally, you classify. Okay, these are the conditions are met. Then your protein, right. This is a kind of transhuman helical proteins, right. They can do that. SVM is support vector machines, right. This I will explain soon. And naive Bayes and k nearest neighbors, k means clustering, random forest, right, artificial neural networks and so on. So, various machine learning algorithms are available in the literature and each algorithm, right, has their own advantages and disadvantages depending upon the problem you choose as well as the input parameters, right, what you use as well as and your final output what you require, right. So, that depends on your problem, you can choose different types of algorithms. So, here I give few examples. The first task is, so we have to discriminate the proteins, right, with any feature. For example, here I used a very simple feature, so that is hydrophobicity, right, that is the only one value, right. Using this one value, how can we discriminate two types of protein, right. Earlier I discussed in the case of TMH and TMS, right, helical proteins are enriched with the hydrophobicity. So, let us see how to use this hydrophobicity, whether we can classify or not. So, we calculated the different proteins. Here I have shown example with 10 proteins. These 5 they belong to TMS and these 5 belong to TMH. How to discriminate, right? For example, we can assign the H values, right? You can set any threshold. For the threshold, you can see whether you can do better performance or not, right? Put a line here. So, how about the prediction performance of TMS? 5 on 5, right, all the 5 we can predict. We can left side see the TMS and right side you can see it is the TMH. Here TMS is 5 by 5, for the TMH 3 by 5, right. Then we can try, we can set different threshold. For example, if you put this threshold, now what will happen? This 5 by 5, 4 by 5, which is better now? This is better, right? Second one is better. Then we try another threshold here. Now what will happen? 4 by 5, 4 by 5. So then the 3 threshold, which one is the best? Second one is the best, right? So we can use your different thresholds and you can optimize, right? See the performance and which one is the best to attain the best performance, right? So you are doing manually, we are doing. So the machine learning, it will take all these efforts and it will tell you, okay, this is the best choice, right? You can go with the highest performance. So here the performance is the prediction accuracy and the key experience is optimizing the hydrophobicity. When they learn the data, so it will finally optimize, okay, this is the best performance you can get, right? If you put one more line here, again this goes, the performance is worse, right? In this case they can optimize, okay, this is the optimized one, you can go ahead with that, right. So now you can use this in classification problem. Then if you go with the real values, for example, if you talk about the protein stability, how far the value changes with H with delta G, right, with this H hydrophobicity, this delta G, we get different points, okay. So now the task is, so predict the stability of the protein. So if H is known, whether we can predict the stability, right. So how to optimize the method, right. So how to perform check the performance, absolute error, for example, if the actual value is 12.5 and the predicted one is 11.7, what is the error? 0.8, right. This is the experimental, this is predicted, this is the error, right, fine. So, now how to reduce the error? For example, if I put a line here, right, here what is the average error? So, from here here is the difference, okay, here this is 0, this difference, okay, here this is the difference, okay, see all the difference from this line, right, take the average, you will get the number. Is it possible to make another line or different other functions, for example, like this, right. So, the machine learning, it will train this data and make this line in such a way that the MAE should be less. So, mean of all these errors should be less, right. This is how it works in the case of the observed values. So, let us example 3. So, if you take the similar types, many proteins, the task is to group similar proteins, right. You can see the similar types of proteins, right, how to classify the similar types of proteins. So, how to assess the performance? You can see the average distance, right, between the intergroup proteins, and that should be minimum. So, if you see this one, you can see, okay, this group is the best fit, because within the group the difference is less. If we go to other group, the difference is more. In this case, this is the group we can fit with the optimally less distance. So, you can minimize the distance between the proteins. For example, if this is the cluster, right, the proteins within this cluster, they have less difference, right, they have similar values. So, there are two different types of learning algorithms, right, we discussed different types of learning algorithms. One is supervised learning and unsupervised learning. What is the difference between supervised learning and unsupervised learning?
So, when previous data is known, then it is
right. If you label the data, so if the result is known, then you can learn as a supervised learning. So, this will have the experience, right, with the known output. So, you can use its labeled data. So, you can train your model, right, to develop your own model. In the unsupervised learning, right, you can, if you know the labeled one, so you can learn by yourself, right, and then see this group should be the probably the similar group, right, like for example, the clustering, right, it will do by themselves. Supervised learning, it will be guided by the labels, right, this will tell you, okay, this is the good way to do that, but this is not a good way to do that, because we know the data. So, you can see the difference. So, then we can optimize the methods, right, with respect to the labels. I will explain some of these methods. Okay, supervised learning, it is a two-step process. The first case, you have to learn using any training data set, right. For example, in the first case, this is your input and this is output. So, with respect to your output, you will map the input data, right, by learning the result from the output, right. So, you can learn and finally optimize. Then we use the same algorithm to test. So, here it is no learning, because now just we have the model, this model is already trained. So, no more learning. So, take any x input, it should give the output, right, then you can compare the performance, right. This is a two-step process. So, different methods available for the supervised learning, right. So, one is the neural network, it is widely used, right. If you see the history of these neural networks, right, they are developed early in 80s, right, mainly inspired by the neurons in brain, right. In the brain contains millions of interconnected neurons, right, which transmit the electrical signals, right, or the messages to communicate. So, what happens in this case, each neuron receives signals, right, through several branch structures, right, and transmits the signals through long action structure. So, this network of neurons, they are responsible for our movement, for example, actions, memory, as well as learning and so on. Likewise, you can use this type of information, right, in the different classification problems, right. For example, take a simple model of a neuron, the kind of regression in the 1D. So, if you take the output is f of z, right, this is connected by different inputs, for example, x1, x2, x3. So, assigned with different weights. So, you can see this w1, w2 and w3. So, the function f of z, this you can write, right, in terms of the weight as the inputs. So, is this equation, right, w1 into x1, w2 into x2 and w3 into x3, right. This can be any decision function, right. So, depending upon your sign, for example, it is a plus, then this is TMS, and it is minus, it is TMS, right. You can use any sign function right, to assign whether this is which class, fine. So, these are the assign weights. With this, along with this assigned weights, we can also use the unbiased weight, like there, for example, this is the W0. So, in this function, so in this case you can rewritten this function y is f of z, this equal to the same, right, plus this f of this W0, this unbiased weight, right, like the constant in the regression equations. So, for example, if you have an AND gate, so output is y, right. So, you can the sign, this is equal to W0 plus W1 in x1 and W2 in x2. So, we have x1 and x2. So, for example, if you take a weight W0 equal to minus 1.5, W1 equal to 1, W2 equal to 1. So, x1 equal to 1, x2 equal to 1, what is f of x? Right, f of x you can use this function, this is W0, this minus 1.5, W1 into x1 plus 1, W2 into x2 plus 1, this is equal to 0.5. So, we get the 0.5. So, you can see a sign minus or plus, this minus or plus is plus. So, this is equal to 1, right. If you take second example, if x1 equal to 1, x2 equal to 0. So, in this case minus 1.5 plus 1 plus 0. So, this is equal to minus 0.5. So, this is in this case minus 0.5, this sign is minus. So, this is equal to 0, right. Next two classes both are minus, so both are zeros, right. You can see with respect to this sign you can decide whether this is TMH or this is TMS. So, how the construct the networks, right, it has different layers. For example, the layer 1, this input layer, right, and this the another layer, that layer 3, this output layer. In between you see layer 2, this hidden layer. So, here this will optimize all these weights. So, we see these are the interconnected networks, x1 and h1 are connected by W11, this layer 1. Likewise, x1 and h2 are connected with, this is a 2 and this 1, this we put 2 1, and this is from layer 1, so put layer 1. So, weight of 2 1. Likewise, is completely interconnected. So, x1 is connected to the h1 h2 h3, x2 is also connected to the h1 h2 h3, and x3 is also connected to the h1 h2 h3. Then see the output. So, from this hidden layer it go to the output. So, in this case weight 1 1 or the 1 2 or 1 3, right, all these 3. So, when we do all these things, finally, you have a decision function, this will tell you whether this is which class, it is the TMS or it is the TMH. How to do that? We can see the h1 is given as this function I discussed earlier. So, here the 1 0, right, this is the kind of constant, we have this 1 x1 x2 x3 with the weights W11, W12, W13 and so on, right, for the h1. Likewise, h2, h3 you can write. Then y you can write a function based on this information, right, W11 and 12 and 13 with respect to the hidden layers, right. So, you can take the function. So, how to get the weights, right, how they learn the weights. So, they learn during the training using back propagation algorithm. So, get the output, then go back, then adjust the weights and see the performance and do it again. So, finally, using the back propagation algorithm, so it can learn and finally optimize these weights, right, in the case of neural networks. Then when it is optimized, then we can use the model for any prediction, right, that is fine. Then the second methods I will discuss about support vector machines, right. What is support vector machines, how it works, right. So, for example, if you see a set of data, right, there are some of the red crosses and some of them are in the green crosses, right. Support vector machine, right, identifies a hyperplane which separates these classes in any n dimensional space. Okay. For example, in these two sets of data, how to identify the hyperplane? We can make a plane, right. For example, if you do it here, right, this will clearly separate. This is the group 1, or for example, to take the TMH and the TMS, you can easily classify, right. This line can be linear or this can be non-linear, so anything. So, then we have see the distance, so how much the width, right, is to have this plane such a way that the width should be the maximum, right, between the two groups of classes, for example, TMH as well as the TMS. So, if you see this, we can have make these support vectors. So, what are the lines which are very close to the line? So, these are the 3 cases in the TMS, and here these are the 4 cases that is very close to this line, right. Then we can decide these support vectors to define the width, right. How to do this? For example, if we take any point, right, any plane in the space, right, here this is your hyperplane, right. So, take a normal vector. So, here is your normal vector, say w vector, right, and then if w dot xi more than or equal to 0, we can take this observation belongs to class 1. See the here you can see TMH, right, otherwise it is a TMS. Then the problem is how to choose this plane, right, that is a problem. So, in this case we have to maximize the boundary. In this case you can minimize this vector w vector, so that you can see the right plane, you remove the planes and then you can see the right plane. How to define the boundaries, right, you can see the support vectors. The support vectors will help, right, to determine the boundaries for assign these boundaries, right. In this case you can define this hyperplane. So, how it works? For example, many times input vector is here, the input vector, right, this is transformed to feature space like Z space. Then you can identify the support vectors of the Zi such a way that this is yi of this w into zi, this is the your support vectors, right, plus b a constant is equal to 1. So, if you define the support vectors such a way that, so yi of this w dot zi is dot product plus b equal to 1, right. Then take the normal vector, it is the sum of the scalar multiples of the support vector w. You take this alpha is constant, z is the support vectors, and take the sum of all the support vectors, right, you get the w, right, this will give you the normal vector, right. Then you have the decision function I of z, this will tell you with respect to sign, right, of w dot z, right, plus b. If it is a plus or it is a minus, you can define the different classes. In the case of linear ones, but they take the nonlinear SVMs, right, they use various kernel functions, right, for the transformation of this input vector, right. So, you can listen lectures offered by the computer science department for more details, right, and the derivations for different machine learning techniques, right. So, we discussed about 2 types of supervised learning. What are 2 types of supervised learning?
Yes.
Neural networks and support vector machines, right. Now, you can see the unsupervised learning. So, it is an unguided learning. So, it is useful mainly this unlabeled data set. So, if you do not know the output, you can for any unlabeled data set you can use that, right. In contrast to supervised learning, here there are no direct measure to evaluate the performance in the case of unsupervised learning algorithms. Then for example, some of these methods are k-means clustering or principal component analysis and self organizing maps and so on. These are the various methods. Let us see how it works. So, we take clustering, this is one of the unsupervised learning. This is very often used for unlabeled data set to group the observation based on similarity. For example, if you have a group of 100 proteins, right, and see the hydrophobicity is your feature. So, all the 100 proteins you know the value of hydrophobicity, right. Then you group the proteins, right, which are very close in the values. Then you move these numbers here and there, so that each group the average difference between the hydrophobicity values are the minimum, right. Likewise, you can cluster. For example, the genes are clustered in the mRNA expression to identify the co-expression genes as well as the proteins. There are various types of clustering techniques, right. Normally these ones are k-means clustering as well as hierarchical clustering. So, now we will see how these clustering techniques work. So, take the k-means clustering, it is robust and it is faster than the hierarchical clustering. Already we discussed about k-means clustering with another application, right. For what application we discussed k-means clustering? Grouping these non-redundant sequences, right. When you use the CD hit, we discussed about this clustering technique, right. So, for this case the number of clusters should be predetermined. We required to tell, okay, we require 4 clusters or 5 clusters, or how many clusters we need. We took group of 100 proteins, if we need 2 clusters, it is simple, you can make a simple cutoff I discussed earlier. So, any specific cutoff you can cluster, right. If you take number of clusters, accordingly you can group based on the values. What does the k-means clustering do? So, it iteratively minimizes the variance within the clusters, right. So, mainly the Lloyd's algorithm is used for the k-means, which is a 2-step iterative algorithm. So, I will tell you how to do that, right. So, if you see is a group of data, right. How to cluster? First see the initial set of clusters, case centers, right. How many clusters we choose here? 1, 2, 3, 4, 5 different colors, right. You can show different colors, 5 different clusters. We set this k equal to 5, right. Then assign each observation to the nearest cluster by calculating the Euclidean distance. For example, if it is composition, we can calculate the Euclidean distance for the different proteins and see what is the values, right. From this you can see what are the nearest clusters which can form in one cluster. Then get the centroids of each cluster as mean of the observations. So, if you have 10 proteins in one cluster, so you can get the average, right. This will be the mean of the cluster. From that we can see what is the difference and what will happen if this fit with this other cluster. So, iteratively it will move here and there, right. Finally, when it is optimized, okay, these are the proteins in this cluster, right. When the algorithm converges, then we will decide, okay, these are 5 different clusters, 1, 2, 3, 4, 5, right. These are the proteins which are belonging to each cluster, that is fine. So, when it converges, then we can see, okay, this is the cluster, we can use these clusters to get the representative set of data, right, for your any of your sequences or any data sets.